Hello, everyone. This is joint work with Aadityan Ganesh, Jason Hartline, and Atanu Sinha. And we're going to be talking about some trade-offs that exist between two quantities, throughput and availability. The main result of this paper is going to be a generalization of the Chernoff band. And it has applications to several different areas in economics. We're going to talk really about two of them, profit inequalities and transaction fee mechanism design. And we're going to introduce this generalized Chernoff bound by way of a toy problem called the soup kitchen problem. Very simple setting. We're going to have a soup kitchen, and every day it's going to make a big batch of kappa units of soup. And diners are going to arrive at this soup kitchen over the course of the day, and they're going to each demand some independent amount of soup from each other that's bounded between 0 and 1. And so, of course, you can sum up these little tiny demands into one giant total demand D. And we, as an auditor of this soup kitchen, are going to care about two different performance metrics. Number one is throughput, and throughput is the fraction of the soup that you make that gets consumed in expectation. So if on average 5 units of my soup get consumed, I make 10 of them each day, my throughput's 1/2. My second quantity I care about is availability. That's the probability the soup kitchen
in this group, so I don't.
It does not run out of soup. That's our availability. We care about that as well. And intuitively, we want both these things to be large, right? If throughput is large, it means we waste very little of our soup. And if availability is large, it means that with high probability, there will be some soup left over when you get to the soup kitchen. And intuitively, they also can't both be bad. You can imagine a day with very high demands overall that you have great throughput, but poor availability, and vice versa for a day with very low demand. Now, that's a very qualitative statement. Can we make it more quantitative?
It's on the right.
So our question here is, we, as an auditor, can we establish tractable lower bounds on these possible availability throughput pairs? So we have an illustration diagram here to showcase this. We have x-axis is availability, y-axis is throughput. And here on the bottom area here is the infeasible region. You cannot acquire alpha taus availability throughput pairs that are below in this lower left region. And that's anything below the solid blue line. So this alpha tau 1 here is impossible. You cannot find a demand distribution where you achieve this particular alpha tau availability throughput pair. And the dashed green line is a lower bound that is known to the auditor on feasible pairs. So the auditor can say, if you hand this alpha tau 1, I know that can't occur. Alpha tau 2, on the other hand, is below the blue line, so it's infeasible, but the auditor doesn't know that. It's above their lower bound. And then alpha tau 3 is feasible, but the auditor doesn't know that as well. So we want to make that dashed green line as close to the blue line as possible. Lets the auditor rule out more pairs. And we accomplish this with our main theorem, which is a concentration inequality generator. It operates as follows. You hand me a function f, and it has to be convex, has to be non-negative, and it has to be increasing past quantity kappa supply. And then for any availability throughput pair to alpha tau, the following inequality holds. 1 minus alpha is bounded above by the expectation of the function f, normalized by f at kappa, where the function f is taking expectation over this random variable x, a binomial, with mean equal to kappa times tau, and with n terms, where n is the number of diners. This should look really familiar. This looks an awful lot like Markov's inequality, but it's not. It's a little bit different. Markov's inequality would have that x binomial replaced with d, the demand distribution, but here it's swapped out, and that's going to make a critical difference. And that critical difference lets us apply it to a couple of different areas. So one of them is multi-unit profit inequalities. These are a mathematical technique that's used to provide welfare guarantees for post price mechanisms when you're selling more than one of the same type of item. And if you have stronger throughput and availability guarantees, that directly translates into better welfare guarantees. So if we have 100 units of soup, it turns out with these bounds that we have, we can get an approximation ratio for post price mechanisms of 0.85. That's pretty good. You get 85% of the welfare. And there exist bounds in literature already on this subject. And if you plug in kappa equals 100 of them, you get 0.62. And this ratio between these two, about like half again of the welfare being captured by R bounds, holds regardless of what the kappa value is. You get to kappa equal to 1,000, 10,000. This seems to be a pretty common trend. So there are constant factors that can be improved here from what is known in the literature. And we also can apply it to transaction fee mechanisms. So Ethereum has blocks. Those blocks have limited space. Sometimes you run out of space in those blocks, and there's an average amount of space on the block taken up. That's your throughput, that's your availability. So you can use these techniques to analyze that as well. So the plan for this presentation, we're going to be talking about the advantages that these bounds have over more conventional tail bounds. We're going to be looking at the two free parameters that show up in that theorem, n, the number of diners, and f, the function we choose. And then we're going to examine a couple of sample bounds that we make, 3 of them, using 3 different f's. We're going to graphically compare how strong they are, see advantages and disadvantages of each. Most importantly, how tractable they are. Some of these bounds will give you closed forms, some of them won't. Stronger bounds might give you less tractable bounds and vice versa. And then we're taking all of those 3 bounds, we're going to benchmark them against what our conjectured true barrier is between the feasible and the infeasible regions. So let's revisit that main theorem again. First off, these aren't really tail bounds. Typically, for the concentration inequality, you have the mean of a distribution, and you ask, what's the probability I fall into some region to the right of the mean? But that doesn't show up here. This holds for any upward closed region. And the upward closed region, I can upper bound the probability of falling in it. So compare that to the Chernoff bound, which I reproduced. Whoops. Didn't go as planned. Sorry about this. Full screen though. There we go. The Chernoff bound here at the bottom is the conventional one, the one that we've all seen and used in various different applications before. And it has this parameter t, which is the distance to the right of the mean before you start bounding a tail region. It doesn't show up in our main theorem. And so that actually matters in some pretty key situations. So on the left, we have a left shifted distribution with this one in blue, where the threshold is to the right of our mean. And on the right, we have a non-tail bound where the mean of the distribution is to the right of our threshold. And so the Chernoff bound is useless in the left case. It's useless in the right case, but useful in the left case. And also it's the case that as you move towards the non-tail bounds, the mean and the truncated mean, which is kappa times tau that shows up in our main theorem, it's further and further away from each other. So the bounds that we're providing are stronger and stronger the closer you move towards non-tail bound cases. So now let's tackle the 2 free parameters. Function f, the number of diners n. We're going to ask which functions f are the best, and also see how the bound depends on the number of diners n, especially if you know how many diners there are. So here's an extended version of this theorem. It's got a lot of different inequalities. We're going to break them down one by one. And the first one we're going to break down is noting that these 2 terms here, that's our original theorem. We have 1 minus the availability on the left-hand side here, and in the bottom left corner there, we have our original side term, our upper bound on the tail / the upper closed region. And we're going to take a look at these horizontal inequalities we've imposed. Now, notice that the bounds on the left, those quantities, are the same as the ones on the right, but we've swapped out that binomial we introduced at the start with a Poisson. And that Poisson is the exact same mean as a binomial. They both have the mean kappa tau. So the only difference is that we've taken the number of diners and sent them off to infinity. And we've gone from these bounds here on the left to these bounds here on the right. So if you don't know what the number of diners is, if you're n agnostic, you can just use these bounds on the right, make them a little bit weaker, and they'll still be valid. And in addition, if you want to find the worst case overall n, you can take n, send it off to infinity, and it would exactly give you these bounds on the right as well. So we both found a way to make n agnostic bounds, and also what the worst case n is. So remember these vertical inequalities here. Notice that these terms here, up above, this one and this one, have the function f in the bound replaced specifically with this term here, the maximum of a linear function, and 0. That's a Rayleigh function. So it's going to be 0 to a point, kind of a kink, and then it's going to become linear with slope 1 past that point. And those Rayleigh functions are constructed from the function f. So what this is saying is that if you hand me a function f and ask me to make a concentration inequality with it, I can find you a Rayleigh function that will be at least as strong. And that holds both in the n-agnostic case and the n-aware case. In other words, Rayleigh functions are the best. They're just going to give you the strongest possible bounds. And lastly, which Rayleigh function are we picking here? We have this beta parameter here, which is the location of the kink in that Rayleigh function. And so that beta is specifically derived to make the Rayleigh function tangent to the normalized original function f, as you can see in this diagram. You can see at that point kappa there on the x-axis, we exactly have the Rayleigh function touching the bottom of the original convex, non-negative, and increasing past kappa function f we started with. And so as you can see, one of them is below the other. And so very naturally, the expectation of one of them is going to be below the other. And that's pretty much a one-line proof of this part of the theorem. So now for our bounds, we're going to look at first bound number 1, which is going to be a non-optimal bound, but it will be semi-tractable. And we're going to pick the function f equal to this exponential function here, which has this very complicated looking term in the middle, but it's really just a giant constant, times x minus 1. This is just an exponential function minus 1. And we're going to insert into our n-agnostic bound. So this produces a strong yet analytically tractable bound. Bound number 2 is going to be, we're going to throw tractability into the wind. We're just going to go with those Rayleigh functions that gave us the most strong bounds possible. And what we didn't discuss earlier was what the best global beta is. We knew how to find betas that would improve over any given starting function f, but not which beta is the best overall. So we're going to fine tune our beta here to get the lowest possible upper bound on 1 minus the availability. So this produces a horrendously intractable bound, but it can be done. You can compute that optimal beta. It's known, for example, that beta is integral valued. So it has to be like 1, 2, 3, 4, and it has to be bounded above by kappa and bounded below by 0. So it's in this discrete range of items. You can brute force check all of them and find which one's the smallest. So you can compute this thing. It just takes a bit of time, and it's certainly not analytically tractable. And 3, we can recreate the classical Chernoff bound using this theorem. Recall earlier I said that our main theorem looks an awful lot like Markov's inequality. Well, you can use the exact same steps as the Chernoff bound proof and just swap out Markov's inequality at the key step where it's used with our main theorem. And it gives you a bound that looks an awful lot like the original Chernoff bound. You can see that these two things here, one on the top is our new bound, one at the bottom is the original Chernoff bound, and they look really, really similar. All we've done is we've taken the mean wherever it shows up in the bound and replaced it by kappa times tau. So this bound is a problem, and we're going to go into it a little bit more later, but it's going to fail at high availability. Yes. All right. Good enough. So first off, let's plot all these things. Once again, x-axis is availability, y-axis is throughput. And the very top one we have here, that dashed orange line, that's our optimal Rayleigh. So it's clearly the best, right? The higher we get these bounds, the better a bound we're getting on throughputs for any given fixed availability. And then below here, we have both the Chernoff style bound and our semi-tractable bound. That's our red and green bounds. Those are really, really similar, like about the same across the entire range of availabilities. But if we zoom in really, really close, we can see it's not quite true. We've just set availability very close to 1 here. We've zoomed in really close to that part of this graph. And you can see that the Chernoff style bound is passing through the x-axis. And that's not true of our other bounds. Those hit 1, 1. What does that mean? What that means is that for very high availability, the Chernoff style bound says the best lower bound I can give you on throughput is negative. And we already knew that. Throughput it's a fraction that's non-negative. So the Chernoff style bound is useless in this case. But the semi-tractable bound we came up with, the red line, which is equally as strong throughout the rest of the range, isn't useless. So this is an important use case. If you do care about this little area here, you want to use the semi-tractable bound, not the Chernoff style bound. And so we can benchmark this against Poisson distributions, which we conjecture to be the worst case distributions of demand for throughput and availability. So we can take the Poisson distribution, take its mean parameter, and vary it from 0 to infinity to draw all possible Poisson distributions, see what their throughputs and availabilities are, and see what that curve looks like. And so that's this. You have this blue line here, which is all of those possible Poisson distribution availability throughput pairs. And you can see it's a little bit higher than the Rayleigh bounds that we get here. So the true actual boundary between infeasible and feasible pairs is somewhere in between that solid blue line and that dashed orange line. And that gap between the that orange line and that blue line, it stays about the same distance as we had from the semi-tractable bound and the Chernoff style bound at different values of kappa. So we just took kappa and we changed from 10 to 100. It also holds that same way if you go to 1,000 or 10,000. It's a pretty consistent pattern. So once again, there's a constant factor to consider here. So in conclusion, if you're looking for tractability, use the semi-tractable bound. You get a minor loss in strength for overall a much more tractable formula. And if you need strength, use the Rayleigh bound. It's very, very strong, very close to our conjectured optimal, though it has a major loss of tractability. All depends on your use case. Hope some of these end up being useful to you guys. Thanks.